So welcome everyone to the European Society of Biomechanics webinar series. And today's topic is why and how to do open and reproducible research. So if you ever wondered why it is important to do open and reproducible research and how to make your research more open and reproducible, you are in the right place. So today, Serena Bonaretti from Belgrist campus in Zurich will answer some of these questions and show you some tools that everyone can use to increase openness. In the last years, she has been dedicating a lot of time and efforts to do and promote open and reproducible research through community service, talks, a very insightful YouTube channel, which I recommend to you all to visit. And on top of this, a free book entitled Learn Python with Jupyter. Before starting, I would like to remind you all that all the webinars from the ESB are uploaded on the ESB YouTube channel, where you can find many other videos, such as recordings of the journal club or awards presentations or plenary lectures. And I would like to encourage you all to subscribe to get to know more the activities within the ESB. Okay, so the presentation will be around 45 minutes, followed by a Q&A session. So during the talk, please type in your questions in the chat or in the question box so that we can collect them and ask them to Serena after the webinar. So I don't want to steal any more time from you, Serena. Thank you very much for being here. And we are very much looking forward to hearing your talk. So I will make you presenter now. And yes, the stage is yours.
Okay, thank you very much. Thank you very much, Chiara, and the European Society of Biomechanics for inviting me today. I am really very excited, very happy to be here, and I'm looking forward to sharing with you my ideas about why and how we should do open and reproducible research. And I'm very much looking forward to your questions afterwards so that we can have a bit of conversation about that. You will find the presentation at tinyurl.com/ESB webinar. It's actually a link that is going to redirect you to Zenodo, where you can download the presentation and you can click the links and interact with the presentation itself. I don't know why my Mac has decided to turn the pages when it wants and not when I want, but let's try. So let's go straight away with the why. Why should we do open and reproducible research? Well, because this is my answer, because I think that openness and reproducibility are the answers to the need of researchers, that is us. And what are these needs that we have? I've thought about three needs, and they are going to be mainly about the musculoskeletal system, the biomechanics of the musculoskeletal system, because this is what I know better, but I hope that you will be able to map that to your own fields. So the first need that we have is to assess scientific claims. And with this, what do I mean? I apologize for this. I really don't know why it's happening. So I will go back and forth a couple of times. If we look into this paper, what makes an accurate and reliable subject-specific finite element model, a case study of an elephant femur, this paper was published in 2011. And what the authors claimed is that they, as you can see here, they wanted to create the first reliable finite element model of the femur of an adult Asian elephant. And the idea was to move forward towards towards a better understanding of the form-function relationship of the femur. And they created three different steps. The first step, they wanted to test out the model precision by conducting a series of convergency tests with regards to the size and the type of elements. Then the second step they wanted to do was to perform a sensitivity study on the model by determining the effects of varying the material properties. And finally, the third, they wanted to compare the finite element results against the experimental data that they obtained. And the final idea was that they hoped to raise the methodological standards in zoological application of finite element models. So pretty standard study from a CT to finite element models with ex vivo validation. So the paper is from 2011 and it gets cited 29 times up to 2 days ago. I did this quick search on Google Scholar. And among the papers that cite that paper from 2011, some of them cite it as part of the literature review. And you know, when we write in papers like it has been shown in previous studies, and then references from 11 to 13, or other papers used it to build upon it. So they actually used the findings of these papers for their own computations. Specifically, for example, this paper from 2018, they used it to create the finite element model, and they said 4-node linear tetrahedra were preferred for FEA, as the previous research has found that such meshes perform well when compared with ex vivo experimental strain magnitudes. And the reference is 24, which is the paper I showed you before. And they continue saying that FEA strain values have been found to converge when element numbers exceed 20,000. And again, the same citation. The little problem here is that 4 years before, in 2014, this article had been retracted. And the motivation is the following. While the model itself appears to be valid, the data taken from it are therefore invalid, as they do not match the location of the region that was experimentally sampled. It was a case of self-retraction, so the authors themselves retracted the paper, and you can read the whole story in this blog called retractionwatch.com, where they keep track of stories of retracted papers. But the point here is not much that we want to be judgmental about the internal situation of the group or the reasons why somebody in the group acted in a certain way. But the questions that usually come up to my mind in these cases are like, what if I was the one basing my research on fraudulent findings? So what if I was the paper from 2018, the one conducting that research? Or how can we base our research, or what if we base our research on involuntarily wrong results? We are human beings, we make mistakes, we might have bugs in our code. How can we make sure that the previous studies are correct? And more, how can we verify that we and our collaborators are producing correct results? It can happen that myself or any of my collaborators, I put my name on their papers, by chance has some bugs or made some mistakes. And last but not least, when we review a paper, imagine the reviewers of this paper from 2018, how can they, excuse me, not the reviewers of the original paper from 2011, how could they know that there was a mismatch between the data used for the two different experiments if they don't have access to the data and the code? The second thing that I think we need as scientists is that we need to build on previous work. Let's look at this example from this paper, Assessment of Reporting Practices and Reproducibility Potential of a Cohort of Published Studies in Computational Knee Biomechanics. In this study, they show, first of all, that the number of publications per year related to computational modeling of the knee has increased dramatically. As you can see, especially in the past, I would say, 20-ish years, the number has really increased. And out of these papers, they selected 9. They selected 9 papers, and there was a major group who organized the study, and then another, I think, 4 or 5 groups. They selected these 9 papers, and every paper was reviewed separately by 2 different groups. And these are the results, some of the results that they got. If you look at this first graph, on the y-axis we have the proportion of yeses of the questions, and on the x-axis the first bin refers or sums up, it's a cumulative count. It tells how many papers actually reported the parameters or all the information needed for the about the study. The second bin instead summarizes if the perception of reproducibility, so if the reviewers actually felt like they could reproduce the paper. And if we disassemble these two bins, we get these two graphs. The reported metric are for the first bin, and the reproducibility metric are for the second bin. And here, if we look, these are the counts of yes to the answers of the questionnaires that the reviewers for this study had to fill out. We can see that they had to check if they had boundary conditions, if there were, they had in the sense that the parameters and the explanation of the boundary condition was complete. The subcomponents intended as geometry, and the interactions. And you see that all of them are not more than 3/4 or 75%. If we decompose the reproducibility bin instead, we see a similar pattern, but what we see is that these answers are statistically significant, lower than the ones of the reported metric. So this means that the authors of this paper really felt that they could not reproduce the paper, the original 9 papers. And so in this case, the questions that we can ask ourselves are, is there a way to document the parameters better so that they can be reused in other publications and other people can build on our work? Is there a way where we can share the code so that other scientists can again reproduce our code and build on top of that? And last but not least, is there a way to stop reinventing the wheel and aspire to a faster advancement of a research field? Every time that we have to re-implement an algorithm already developed by another lab, we're kind of wasting time in the big picture of advancing the field. The third and last need that I want to mention is that I think as scientists, as computational scientists, we need to compare and validate the algorithms that we use. And let's look at this paper, a round-robin finite element analysis of human femur mechanics between 7 participating laboratories with experimental validation. In this paper, they prepared a frozen human femur for a compression test, as you see here, and they did the usual strain measurements and so on. And then they put all this into a computer, in a computed tomography scanner, and the data together with, it was scanned together with the calibration phantom, and the data, the images, as well as the orientation of the bone was together with the boundary conditions were delivered to 7 participating laboratories. And these laboratories had to perform a finite element analysis that simulated the experimental setup and send the results back to the coordinator without knowing the real results that they got. And what they found here is that out of these 7 laboratories, 4 had deviations of less than 40%, and the other 3 had deviations of more than 120%. And the others here conclude that it was shown that the precision of finite element models of the human femur is not yet as developed as desired by the biomechanical community. So in this case, we can say, okay, is there a way that we can compare algorithms easily, not specifically for this study, but in general? And once we have compared these algorithms and we find the good ones or the best performing ones, how can we standardize the procedure across laboratories so that we can all use them? And again, how can we collaborate together for a faster and greater advancement of science? So far, I have showed you 3 different needs that I think we have as researchers. First, we needed to assess scientific claims. Second, we needed to build on previous work. And third, we need to compare and validate algorithms. And I really think that working in an open and reproducible way is the answer to these needs. So how? How can we work in an open and reproducible way? There is a lot of fuss about all this, and I'm going to try to give you my ideas to streamline a bit the ideas. When I think about the output of my research, I think that there are 3 main components: data, code, and publication. And these 3 components, of course, are intertwined to each other, but we can analyze them separately for easiness. So if we start with the data. When we talk about data, we talk about, in case of finite element models, for example, we talk about meshes, about boundary conditions, about images. When we talk about metadata, we talk about the information about the data. And I'm going to tell you a bit more what I mean with that in a second. The first thing that we should do to work in an open way about the data is to use open file formats. So at least when we release the data, we should use the CSV files instead of Excel files, because not everybody has a Microsoft license. The second thing we should do, we should specify data provenance as part of metadata. When we work with data, we deal with both raw and derived data. So raw data, again, can be, for example, a CT image, and the derived data can be the mesh created from this data. And it's important that when we put out there the mesh, we always provide both the code and the information about where this data is derived. And last but not least, it's important that we provide a license. Maybe not everybody knows, but online material is automatically protected by copyright, which means that every time that we put something online, we cannot, if we use, or like if we put something online, other people cannot use our material because it is automatically protected by copyright. If we want other people to use our material, or we want to use other people's material, we have to provide a license. And for data, the most common license is the Creative Commons licenses. You might know them maybe from when you publish your papers, but the Creative Commons licenses are actually very easy. They are made out of 4 different symbols that get combined differently depending on what you want to achieve. There is the BY for the attribution. There is the non-commercial. It means that nobody can create, can make money out of the data that we provide. The non-derivative, it means that nobody can create further data from the one that we provided. And the share alike, that means everybody who uses our data and creates something new with that has to have the same license as we put. And then there is also the public domain, which is basically, this is my data, do whatever you want with it, no copyright, nothing, you don't even, no license, nothing, you don't even have to say that it was data that I provided. Once it's clear how to handle the data, we have to put them on data repositories. And there are at least 3 different types of data repositories. The first ones are the institutional data repositories. Here, as an example, I put the PUB data from Berlin, and they have images from their own groups about spine and bone, for example, and long bones. There are topic-specific repositories. For example, OpenNeuro is a big, at this point, database that collects brain images from all over the world. And then there are generic repositories you might know of, heard of, Zenodo and Figshare, that there are just basically drop boxes. You just put the data from any different possible discipline, and the metadata that they require are generally very broad. If you have to decide where to put your data, my recommendation is to have a look if there is a topic-specific repository, something where your colleagues already put the data, because these repositories are the ones that have more detailed requirements for data and metadata, and this implies that they favor a standardization across labs in the same field, so that your data can be reused easily from other members of the community. Why should we use data repositories? Why cannot we just put our data on Dropbox and put the link out there? There are at least two good reasons. The first one is that it is known that personal repositories often get deleted, and so the links might be that. And the second is that these institutional or established repositories provide a DOI, that is a digital object identifier, a unique number that identifies your data. And this means that people can cite us. You see, for example, if you want to cite all versions, Zenodo tells you how to do. But it also helps us with version control. It means that we can keep track of the different versions of our data set. This was for the data. And now let's look into the code. For the code, it's gonna be a little bit longer because I think that there are a little bit more things to do. And I would like to talk about the three main aspects. The first one is that we should use the open source programming languages. There are plenty of open source programming languages. The most famous ones, I think, at this point are Python, R, Julia. And a lot of people ask me, which one should I use? The one that meets your needs better. I don't think that any of them is better or worse than the other. I think that really it's about sharing code with people in our own field. So if the other people in your field use Python, go for it. If nobody else in your field is doing open science yet, just look at the packages, at the code that is out there, and the code that you can reuse from generic packages and build on that. How to transition? This is another very typical question I'm asked, because how can we, some people tell me, for example, I'm used to code in MATLAB. Is it difficult to move to Python? There is a bit of learning curve, of course, like in anything else. The point is that from my personal experience, the easiest way to do this is to translate from existing code. If you take a little piece of your MATLAB or whatever other commercial programming language you use, and you translate the algorithm to a new, to what for you is a new programming language, you will focus only on the syntax of the language and not on the algorithm itself. And this is gonna make it much easier, because it's really like translating a text that is already written from, I don't know, Italian to English without really having to think about what is written in there. Then another very good way is to use online material. There is plenty. If you prefer more structured material, I highly recommend open free courses on Coursera and Udemy. If instead you prefer to cherry pick the information that we need about some specific aspects of what you have to do, there are plenty of blogs. I enjoy particularly, for example, Geeks for Geeks. I find it very convenient and easy and streamlined and with a lot of good examples. Medium, where people blog and post code and also how-to series. YouTube, if you're more of a visual or video person. YouTube, of course, there are plenty of information. And then something I used quite a lot at the beginning were also cheat sheets, those tables that collect the main commands so that at least you can learn how to navigate. And then the great advantage for me when I transitioned from MATLAB, for example, to Python was Stack Overflow. The cool thing is that since these languages are so broadly used, not only by a specific community, but way, way broader, every time that you have a problem, there are at least 5 people who have had the same problem before. And so just by searching for it, usually Stack Overflow proposes an answer, and I try usually 2 or 3 different snippets of code, and the answers are there, and the production of code, the creation of code is much, much faster. And then there is also some contribution that I made, as Chiara mentioned nicely before. I am writing a book that is open and free. It's called Learn Python with Jupyter, and it is half written. The other half is coming. I upload a chapter every 4 to 6 weeks. And I have a small series also on my YouTube channel. The other thing that is super important is that when we write code and we want to share it, we have to write it for other human beings. So it is important that other people can read, understand the code that we're writing. And so it's important, fundamental, to write documentation and keep a standard style of writing. So for a style guide for Python, there is this peps.python.org, where it really says, all the variables have to be lowercase and so on, so that people can identify the different components of the syntax of the code very easily. On the other side, for the documentation, the NumPy documentation guide is fantastic, and it's based on docstrings. After you define a function, you usually put these 3 times or 3 times double quotes, and for every function you put first what the function does, maybe an example, and then the parameters that are the inputs, and then the returns that are the outputs. And through available tools, you can get directly web pages that you can share and people can use to understand your code and the functions that you have written. And then, last but not least, it's important, again, here, as we did for data, to put licenses. Just putting our code on GitHub, for example, is not enough because it is automatically protected by copyright. We have to define the license. For code, there are 2 main types of licenses, permissive and restrictive. In both cases, anybody can reuse our code. The difference is that in permissive licenses, the person who reuses our code does not have to keep their code open as well. Instead, in the restrictive licenses, they have to keep the code open. And if you need more resources about what licenses to use, there is this great website called chooselicense.com, and in their appendix there is a very long table. This is just a small screenshot where each row is a license and each column is a characteristic of the license. And based on this kind of table, you can pick the license that you need. And I also have a video about that if you prefer a bit more of an overview. The second aspect that I think it's fundamental for code are the computational narratives. And I am honestly a little bit obsessed with this. I know that they are a bit controversial. Some people are not very much into computational narratives, but for me, they were a game changer because they really allow us to tell stories, and they are mainly made in Jupyter Notebook. I'm talking about the Jupyter Notebook and R Markdown. Markdown, they're called Vignette very often. And they are these great web-based tools that allow us to integrate narrative, images, equations, and code. And they are great to draft code, to write reports, to write use cases, and as the creators say, they are also great to make the coding processing human, because it's really an interaction between us as human and the machine creating something, and then we are not satisfied with that, we give another input to the machine and so on. It's really a conversation with the machine that helps us also think better about what we are doing. these kind of computational narratives are I think that they have two aspects that are very important and that they should be very well structured, and they are narrative and code. I see sometimes, very often actually, Jupyter notebooks on GitHub that have no narrative at all. And I think that that is completely useless, because just putting code doesn't make sense in a Jupyter notebook. Just put it in a normal script file, in a .py file, and that's fine. What the strength of these tools is actually the narrative, and it would be great to have it structured properly. From recommendations from the literature, which I provide at the end of this presentation, the recommendations say that we should, at the top, write the title, authors, licenses, and then write down the aims of our notebook and the table of contents, if available. And then it's important to divide our workflows in paragraphs that have titles. And before each code of cell, each cell of code, we should introduce the code coming below, why we're doing that, what that is doing. And after that, we should comment the results. Doesn't always have to be a very long novel, you know, it can be just a few lines, but at least this integration, it's written for humans. And the second thing is that it's very important to structure the code. For example, the package imports should all be at the top. They should not be spread out within the notebook. The functions, again, should be at the top. Then there should be the variables, and then the workflow body, and then the dependencies, about which I'm going to talk in a bit. What we did within the ORMIR community, which has been around for 3 years, and I'm going to talk about it a little bit later, we created a template within our community, and I really recommend you to kindly ask you to download it and try it out and give us feedback. The idea of this template is really on structuring the code, the narrative and the code of a Jupyter notebook. And exactly like when we write a paper for a journal, we download the template of that journal, and it helps us at already having everything structured so that we can just fill in the different paragraphs. And so this is the same idea that we have here with this Jupyter notebook template. So please download it and give it a try, and let us know what works and what doesn't, so that we can improve it. The third thing that I think it's fundamental in coding for openness and reproducibility is to create reproducible computational workflows. And with this, I mean that we should press a button, and that button should go from uploading the data to the final result, which usually is a graph, a table, or some other products saved on disk. There are at least the 4 steps here that we can do. The first one is that we should automatically download the data from a repository. Let's say that we've put this file on Zenodo. So what we want to do, if we work in Python, is that we want to import this tool called wget, and then we write the file name if we want, and then the Zenodo URL. From this Zenodo URL, what you have to change are only these last numbers that are the last digits in Zenodo's DOI. And then wget.download Zenodo file name and local file name. And the data are automatically downloaded as soon as you run this cell. The second thing we should do is that we should avoid manual intervention for data analysis. When we have the Excel files or the table or other tabular formats, of course the CSV would be better, we should not touch them, because every time we reshuffle some data around or we do some computations there, we could potentially add human error. What we should do is that we should upload this data on Jupyter, for example, or any code, and then programmatically do the deleting and the cleaning using the packages pandas or tidyr, so that it is reproducible and we don't touch the raw original data. The third thing is that if we have any random procedure within our code, we should put random seeds. You see here the commands for Python and for R. These random seeds are basically the seeds for the pseudo-generating algorithm of random number and for random numbers. And so every time we have this, we create the same random procedure that can be replicated and reproduced. And last but not least, what I was mentioning before, the dependencies. So the dependencies are basically the printout of the versions of libraries and the machine characteristics. In Python, one useful package is called the watermark, and you have here the commands in case you use Python. If you use R, there is a session info. And basically what they do, and they're usually put at the very end of a notebook, is that they print out the characteristics of the machine, and mainly the characteristics, the version of the packages, both of Python and also of the packages used. And this is fundamental because all this code that people are creating with Python, R, and so on is all work in progress. And there might be changes and there will be changes. And we want to make sure that we are able to reproduce our results. And just this simple printout with the version of the package that we used can help us at achieving that. And again, if you want to see this in practice with a real example that you can also download from GitHub, I have this video. And then another two very quick best practices. The first one is that we should work in version control, GitLab, GitHub, Bitbucket, choose whatever you want. And the second is that code can be cited. We can link our GitHub repository, if we use GitHub, to Zenodo and get a DOI that can be used for citations. So not only we can get our dataset cited, but also our code and of course our publications. And here you see again a GitHub post on how to do it and a video on how to do it empirically. And last but not least, the third output of our research are publication. And nowadays, we all know what open access is, and we know we have to, share our work openly, at least the report. And how do we do it? Well, there are preprints, bioRxiv, archive, now there is also medRxiv, and so on, that allow us to release fast while we wait for the peer review process. And then when we go through the peer review process for traditional journal, we can opt for open access possibilities. Of course, they're costly, but more and more national funding agencies support these kind of costs. But there are also other journals that are coming out more and more, so keep an eye on them. There is, for example, the Journal of Open Source Software. If you create a package in R or Python and you want to publish it as a package, JOS allows you to write basically a 2-page report that is your publication, and they really check your code. So it's not only help you at testing it, at building up your GitHub README file. So it's not only publication, but it's also learning experience that helps us at standardizing our code and have it used and reused. And similarly for data, there are more and more journals for specifically to publish scientific data sets. But I think that for publications, we can do a step further, and we can make papers interactive and reproducible wherever possible. For example, we should provide all the information about the data and code that there are in our publication. For example, for software and for data, we can specify the repositories, so where to find them, where the documentation or the metadata are, what kind of software or language we used in case of software, the licenses that we used so that other people know how they can reuse our code or data, the DOI of our material, and the citations. It's important to provide citations because sometimes people want to cite, but they don't know how to do it. So if we tell them how to do it, we make their lives easier and we get more citations. And then it would be great to have more and more to facilitate the reproducibility of the analysis. For example, it would be great to have results, and then we click on the result and we get directly forwarded to the notebook or the script that allowed the creation of that result, so that we can reproduce it and test it and reuse it for our studies as well. And similarly for the figures, because at the end, the figures and tables really are the core of our results. And so we want to make sure that the information that is in our figures and tables are actually correct. And then there are more and more tools like CurveNote, which I've got to learn a few weeks ago, where basically you can integrate a notebook. You see here a Jupyter notebook with the graph, and then they provide an interactive, they provide a text editor where you can actually embed the graph from the notebook, and you can interact with it. And if you change the notebook, the editor will automatically also change the figure in the notebook. So it's a time for the last considerations. We had a lot of questions at the beginning, and I hope that I convinced you, or at least I gave you some suggestions, that going open and reproducible is the way to go. And it's a way for us as scientists to actually do what is useful and needed for us. It's not just a request from the top, because actually all this started from the bottom. It was a movement from bottom up, and things are actually changing. And if you think that about a month ago, the White House in the United States, together with the federal agencies who fund the studies in the US, declared 2023 this year as the year of open science, it means that things are actually changing, that these things are becoming more and more important, and they are taken into account. So we have to know how to deal with them, and we have to do them. And for example, NASA as well. I know this is the European Society of Biomechanics, so I should have looked better for European examples, and actually Europe has done already a lot, and even before the United States. But I think that these are of great impact. And NASA has just launched this program that is going to last a few years, and that is called the TOPS, and that is an acronym for Transform to Open Science, and they are both creating learning material to help researchers, scientists create work in an open and reproducible way, and they are also working on making their tool open and reproducible. And then the other important thing that I think is fundamental is that all this might feel overwhelming, but it's not. It doesn't have to be, because you're not alone. There are a lot of communities out there. You just have to look for the one that fits your need. In musculoskeletal imaging-based research, we created the open and reproducible musculoskeletal imaging research community called ORMIR. We have been there for 3 years now. We changed the name. We're organizing ourselves better and better. And as I showed you before, we have created, for example, the template, but not only, we already have 2 packages that are out there, ready to be used. One is called the Cyclope, and it is a computed tomography it goes from computed tomography to finite elements, the whole pipeline. And the publication has just been accepted on JOSS, the journal I mentioned before about open source software. And then the other one that we created is called ORMIR XCT. If you work with SCANCO or high resolution peripheral computed tomography, quantitative computed tomography images, this is a package that is gonna help you work in an open way to process the images. And this is still under development, and it's gonna, I think they just submitted to JOSS as well. So there is, and these 2 packages were developed around a Jupyter community workshop that we organized last June in Maastricht. So there is a lot going on, and please, if you're interested, if you do MSK imaging research, based research, join us. We are work in progress, but I think that anybody can help, and even a super small contribution. It can be for meetings, it can be for creating learning material, writing code, organizing again the meetings, anything works. So I would like to go towards the end of my presentation with these conclusions. I really hope that my message is clear, that open reproducible research is a way of working that supports researchers' needs, is not just something to be done to make somebody happy. And nowadays we have all the tools to do open and reproducible research. All the infrastructure is in place. Some of it, it's not ideal yet, but it's all there. And finally, you are not alone. So it doesn't have to be perfect. Anything you do doesn't have to be perfect. It's a learning process. It's a learning experience. It's going to take a little bit, but it doesn't matter. Just start. Here are some references that I used to create this presentation. And I would like to thank you for listening and the European Society of Biomechanics for giving me the opportunity to share my thoughts. And now I'm really looking forward to your questions. And I'm gonna switch on the light, I think.
Thank you very much, Serena, for this great talk. And really, thank you so much for sharing all your knowledge about open and reproducible research. I think for many people, at least for me, I wasn't aware of many things, and especially of many tools that are already out there. And also you explain them in a very easy to understand way. So thank you. And yeah, I think many people will be now inspired by this talk. And I think maybe they need also they need to listen again to this presentation to absorb all the information. But luckily we will upload it. Yeah. But yeah, we will upload it so on YouTube so everyone can have a look again. So yeah, while we wait for answers from the audience, I can start because I was actually particularly interested by the fact that we can also get codes and data cited. I wasn't aware of it. And I was wondering regarding data, for example, since we often aim at building patient-specific models. And of course, patients' data are protected by privacy. So how can we handle these?
Yeah, this is a very controversial topic. There are a lot of different directions to manage this. The most important thing is that, first of all, the patients in their informed consent provide consent for open access. So it has to be written in the informed consent. Mm-hmm. Secondly, it's important to anonymize the data. So we have to make sure, for example, in the neuroimaging repository that I showed you before, they have to crop away the face when they provide the images of brains, because of course you don't want that people get recognized from these images. So anonymization is a very important step. And then there are a lot of different ways to share. There are embargo periods, if this can help. There are also, I've seen, for example, the ZIB a repository that I mentioned before about bone images. Some repositories ask to provide a little abstract of what you're going to do with the data, so that they can also keep track of where the data goes and that they get the proper citations. So I think that these are all things that are slowly getting in place, but to share data from subjects, it is important that they provide consent.
Okay, thank you. And I actually see here a questions. So the audience is wondering if there are open and reproducible communities specialized also in other fields such as gait analysis and tissue engineering. So do you know if there are this kind of community out there?
Yeah, so I'm not super sure because when I look on how to create the community and how to keep it going and what the others are doing, I actually base a lot my knowledge and on communities in natural sciences. They are much more advanced than us because if you think about people who study oceans, the water goes from I don't know Italy to Greece, and so the Italian community cannot keep the data there, and then the Greek cannot keep the data there. They need to exchange the data. So just by definition of the job, by needs that they have already in place since decades. Okay, we are new in all this, but they have already everything in place. For gait analysis, the only thing I know is that there is the tool OpenSim, I think it's called, where they do the simulation. That is a tool for simulations, and I think that there is a lot of open science going on. It is open source and open itself. For tissue, I don't really know.
Thank you. I think you answered very well the question. Another thing that I was wondering is, nowadays we see, as you also told us, we see an increasing tendency to switch towards open source softwares and programming languages, but many labs are still using not free softwares and programming languages, and sometimes it's also difficult for new researchers coming, since they start working with previous codes, previous models. It's difficult to maybe start using a completely different software and translate the code and so on. So what could help in this situation, in your opinion?
Yeah, so I think that, it's a transition. You cannot like spend the first year of your PhD translating somebody else's code, right? This doesn't make any sense. So what can be done? There are a lot of ways to make different programming languages talking to each other. In the worst case scenario, you save the output on one piece of the pipeline written in MATLAB, and then you keep going in Python, So the transition can be done smoothly and step by step. I strongly believe that it cannot be done perfectly right away because it takes way too long. It's a working process, and it might require maybe a few generations of PhD students, maybe 2 or 3 generations of PhD students within a lab. But I think that it's a process, and I think that also for MATLAB code, for example, there are wrappers. You can create the executable and call the executable, and that's it. If you needed to instead work on the code, again, there are tools that allow MATLAB and Python, which are not that different from a syntax perspective, to talk to each other.
Okay, good to know. And so probably it will take still some time to get to reach a fully reproducible research, and probably we need more generation working together. So do you think that
Sorry, it's important to start,
Yeah.
Because the more we wait, the later this happens.
Yeah. And do you think that apart from this, there are other obstacles in the, let's say, in the development of this more open and reproducible research world?
Yeah. So an obstacle is there I see 2, at least, that I think should be addressed. The first one is that writing the documentation aspect requires a little bit more time. But also internally within a lab, if one again, works, for example, in MATLAB, just because it's the one I know, not because MATLAB is the devil, the other way around, absolutely. But if, you take the code from the previous PhD students or from a PhD student or another postdoc or so, you need some documentation. So that is independent of the language, of the programming language that you use. It's really the passage of information from one generation to the other. And this takes time, and this is often underestimated or underused in labs, and I think this delays in general. The second thing, I don't remember what I wanted to say. The question was the difficulties about, sorry.
The obstacles that you see in this path towards reproducibility and openness.
Yeah, I had another one. Okay, it will come back.
Yeah.
Sorry. Let me think. Completely blank. It will come back.
Yeah. And so I don't see other questions from the audience. But yeah, I would have a lot of questions. I think really you showed us so many different ways from which we can actually start. And so, for example, another thing regarding publications, I didn't know that we could include all these little figures that are connected to our data or licenses and so on. Do you know if this is possible and available for all journals, or of course, maybe they have to be open access, or also maybe no?
No, it's a link. So as you have the link in the references, the publications in the references are linked to another website. It's a link. In the preprint I made for the one I showed you, I put the little icons just because I was having fun, let's be honest. But then in the actual publication, I put text, like data on Zenodo here, kind of thingy, and then that here goes to the link to, of course, for the electronic version, not for the printed version. So it's not it's any super simple link. Doesn't need to be anything special.
Cool, perfect. So I don't know if the thing you wanted to say came back or not.
No, but another thing came up to my mind, that is any of you who has questions, please contact me. I'm really very happy to share what I know and support in any way I can. My email address is serena.bonaretti.research@gmail.com. I am on Twitter. I am on YouTube as at Serena Bonaretti. So really don't hesitate, any of you, to contact me for any questions you might have.
Thank you very much for your availability, and I really recommend you all to go and watch her YouTube channel, because you can find a lot of information also there. And it's the videos are
not the best ever, but the content is there. Let's put it like this.
Also, the animations are amazing, so it's really easy to understand. So I think we can close it now, and I would like to thank you very much again for being here, and it was great.
Thank you for inviting me.
So bye-bye, and have a nice evening, you all.
Thank you. Bye-bye.